Saya tu?哦，中文考试，考试我们不是用掉一节吗？对啊，我怕了来不及。嗯，是以前我们考试就是吃掉一节就吃掉了。这一科比较难，我怕等下来不及。Hey, you can eat. You can in the class.
So, sir, how was the midterm exam?
How was the midterm?
Are you having a
Not really, because I know it's going to be hard. So I know what I want to expect, but yeah,
is it very hard attack or just
not really a hard attack. Not really hard attack. It's kind of expected. Yeah, but assignment, I have a lot of hard attacks because that one is like given time to do, but still not good. Like exam is different. Exam is limited time and then no resource. So that one is expected if you don't do good. But if assignment, I give you time, you can search for it. Still not good, then that one I really hard take. You understand or not?
yeah.
Yeah. So don't do assignment, do like you are as in you are having tests. It's wrong. Different concept. Yeah.
Because one is
Yes. Yeah. But yeah, so you need to arrange your own time now. Hopefully I can return your big term on Wednesday. we can discuss about it. Because there's still one more person who haven't yet. We'll talk more about midterm and then discuss about the solution together. Okay. Okay, so today we have this replacement class is replacing the midterm exam because midterm exam took up one class, one lecture. So I scared that we are behind the schedule, so I think it's better for us to do the replacement class. Okay. So what are we gonna to do today? So we're gonna continue with compactness. Okay, we're continue with compactness. So let us recap what is compactness. It is a topological space compact. Anyone remember the definition? So a topological space is compact if every open cover, okay, we want to cover it with an open set. Every open covering of X has a finite subcover. Okay, no? So if you want to show that a topological space is compact, you need to start with any open cover, and then you want to find a finite subcollection that also cover your space. If you already start with a finite open covering, then it is already finite. So you need to consider also infinite covering, open covering for X, and then see if you can extract out a sub collection of it to cover your space. If you can do it, then the space is compact. Does it make sense? Okay. Okay. Good. So let's do one exercise for today. Yeah, I want you to think about how to prove this statement here. So opening exercise for today, show that the continuous image of a compact set is compact. Okay. Try think for 3 minutes how to prove this. I'll say this proof is like a few lines. So try and think about it. Have we proven any extreme value theorem yet? No, right. So I only introduce you this definition, so just use definition. Is enough. What part you don't understand? Yes. Then you want to prove this compact, say who is compact now? Compact set is compact or continuous image is compact? Yeah. So I didn't say continuous image is compact. I just said continuous image of a compact set. So you have a compact set, and then you use a continuous function to map it. Image is compact. You can try discuss with your friend. Okay, so how should we start? So what do you want to prove here? We want to show that if f from x to y is a continuous function, okay, and you have a complex subset in your domain, then fa is in y. So you can realize that this A as a subset of X here, right? It could be the whole space if the X is compact. And so we consider any compact set inside your domain. Everyone agree this is what we want to prove? Okay. So to prove that FA is compact, what do you need to do? Every open covering of FA, you need to prove that it has a finite subcover. Okay. So since you need to prove for every open covering, right? Then you need to suppose there is a open covering for FA. Right. Start with arbitrary open covering and then show that it has a finite subcover. Right. So now, so suppose C is an open cover of FA. What does the open cover mean? FA can be written as the union of open set in C. Sure, the open set is also open in X, right? But we have picked out a collection of open set in C. Okay, so C is a collection of open set in X, such that FA is the union of all the open set. Make sense? Does it make sense? Okay. Then what? What can we do to this C? We can look at the pre-image of C. What are the pre-image of C here? Looks like. Also a collection of open set. Why? Why? V is in C. C contains what? Open set in X such that the union is FA. So now I take F inverse of an open set. Open, is it still open or not? Why? Because F is continuous. So this is a collection of open set again. What So what other property does this set holds? It is also an open cover of air. Why? Anyone know why? Because, let me write here. FA equals the union of all V, and then we can just take inverse image on both sides. Okay. But do we have equal sign here or not? Do you remember if we apply inverse on both sides, do you have equal sign? Or equal sign or not? Let's check. Okay. Wait, do you have equal sign or not? Yes. I remember one side we don't have equal sign, right? So let's check. So do we have equal sign if we apply F inverse? So F inverse on the union we have equal sign. But F inverse on the set, we don't really have a equal sign here. Does it make sense? And this one has to do with the surjectivity of the map. So on union, it is equal. It is distributive. Okay, but if you apply F inverse on Fx, there's only one side inclusion here. But it is enough for us already. Right? It is enough for us. So what do we get here? So we really get A is in the UI F inverse of VI. Okay. Okay. Make sense? Okay. So meaning potentially this F inverse, right, might contain more stuff than A. Okay. But A is there. So what can we do here? What can we do here? So this is an open cover for A. But what's the assumption on A? It is compact. So what does it mean? Since what? Since A is compact, there exists a finite subcover. Let's say F inverse V1 until F inverse Vn. Okay? Covering A. Make sense? Making sense? Everyone follow? Okay. Then what can we do? So this means what? This means what? This means what? A equals to union of F inverse of Vi, where I is equals to 1 to n. Okay or not? Okay. Are we close to the answer already? What can we do? We can apply the distributive law again, right? Such that A is equal to the inverse of the union of VI. And then, what does this mean? A is the pre-image of all these things. So what's the image of A? You just apply F on both sides. Okay, if you apply F on both sides, what does it mean? This implies that FA is equals to the union of finitely many VI. Okay, does that make sense? Okay, so we have found a finite subcover for FA, okay, by using the compactness of A. Any question about this proof? Feel free to ask it, because there's nothing secret here. Any question before we proceed? Okay, if not, let's continue. Let's continue. So last time, what did we discuss last time? We discussed that the closed interval 0 to 1 is compact or not compact? It's compact. Okay, and then we asked whether a subset of a compact set is compact or not. But we found that the open interval 0, 1 is not compact. But we haven't really shown the closed interval 0, 1 is compact. Right? We just mentioned about it. Okay, we haven't really shown it yet. You guys seen it in the MA2 course? Yes. What's the compactness definition you guys use? Closed and bounded. Okay. I mean, what's the compactness definition you guys use? Same using open cover? Sorry. Cover is what? What do you mean? Doesn't make sense. You guys also use open cover? Or you guys use a sequence or not? Every sequence has a convergent subsequence. No, not using that. Wow, so advanced. Because last time when I was introduced to compactness, we use every sequence have a convergent subsequence first, and then only use this open covering. But in our course, we will look through all of this together and then show equivalences between them. Okay, so last time we mentioned about a closed interval 0 to 1 is compact, and then we said that we will prove it later. So we'll prove it today. So in fact, we will prove it for any closed interval. A from A to B is compact. Of so let's specify the topology. So we call it a Euclidean line. Okay. Okay, so how are we going to prove it? So we will just prove it for closed interval from 0 to 1. Okay. Because you can build a homeomorphism between the two closed intervals. For any closed interval, AB to 0, 1. Right. Last time we talked about this. You can use the bijection that we have from showing the cardinality. You can check that it is a homeomorphism. Is it okay? Okay. Please write down the homeomorphism. If you don't understand what I'm saying, try write homeomorphism here. Do you still remember what's a homeomorphism is? What's a homeomorphism? Bijective, continuous, and the inverse also continuous. Okay, so you need to produce this map. Okay. So since AB is homeomorphic to 0, 1, so it suffices to show that the closed interval 0, 1 is. So how to show set is compact again? Remind yourself the definition again. How do you do that? Hmm? What's the definition? What's the definition? It's okay, change to 0, 1 interval. I don't want X. I want 0, 1 now. Close interval 0, 1.
0, 1,
Yes. Okay, so you need to start with any open covering for close interval 0, 1. And then show that it has a finite subcover. So similarly, we will suppose C is an arbitrary open cover of 0, 1. Okay, close interval 0, 1. So you need to specify close or open because there's a lot of 0, 1 interval. Can be half open, open. Okay, but we are looking at close. So what is our goal? We want to show that we can cover the entire interval 0, 1 with a finite sub collection from C. Okay. So how should we think about this question? So what's the picture appear in your mind when I mention the closed interval 0, 1? What's the picture appear in your mind? What's the picture appear in your mind? 0, 1. What's the picture? Any picture in your mind when I talk about closed interval 0, 1? Yes or no? Yes. So what's the picture appear in your mind? Hello, hello. Yes or no? Yeah. So what's that? Can you describe to me? How should I? Can I draw it or not? So how should I draw it? Sure. Let me draw a straight line. So I put a 0, 1, 0, and 1. So the interval is all the points in between 0 and 1. Okay. So how am I going to find the finite subcover here if I given any covering? How should you think about it? So if I have open set in we prove that open set in a real number is what? Countable family of disjoint open interval, right? Non-empty interval. Okay, so maybe we want to cover with some infinite open interval like that. But how can you always pick a finite subcover? Do you think so? If I have infinitely many open interval here to cover my closed interval, can I find finitely many open? Cannot. How? What do you mean by that? How could a one interval contain only one point? By density of rational number, right? You must add irrational. Sorry. Right? What do you mean? I mean, if you have infinitely many open interval here, can you find a finitely many to cover this whole interval here? Can you do that? Why not? Why? Why not? You need to argue, right? Mm. Mm. And then, and then, and then, and then. But remember, my theorem is to prove it's compact. That's mean cannot. If you want to argue cannot, then maybe you are wrong. Correct. So my question is, given infinitely many open set that cover the closed interval 0.1, how you find finitely many of them to also cover the closed interval 0.1? Hmm? What do you think? Huh? What can you do? You can start with a covering on the left hand side, right? First, right? Okay. And then you can find the next one. Possibly overlap with the first one, right? Okay. And then you keep going. But the problem here is why is finitely many of them enough? How to cut who? Okay. And then
So such that
then
and then less pieces with
you mean the leftover one, you just union all of them. Another open set. Is it? Union the open cover. Okay. So remember, what is the open cover again? You are a collection of open set such that if you want to cover A is contained in the open cover. Okay, might not be equal. It just contained. Contain. Otherwise, how we use open set to get this closed interval, right? Okay, we must be able to just contain. So what's the trick here? So what's the trick we're gonna use here? Actually, we're gonna use a trick which is supremum. Okay. So sure, we need to start somewhere. Okay, you can start with one. You can start with any point inside there, but we choose to start with to cover 0 first. So first, choose C1 in C, which contains 0. Okay, so we choose C1 like this. Okay, we choose C1 first. Okay. C1 in C, which contain 0. Okay. And so what does this C1 do? Then C1 will contain what? Will cover part of the interval, okay, to some epsilon, depend on this interval, okay, for some epsilon. Does it make sense? So where's the epsilon here? So epsilon is here maybe. Does it make sense? Okay, cover to some epsilon. And we want to see is so what we did just now, right? We already cover up to epsilon here because we have an open cover that cover every point. So at the epsilon point here, we should have a open cover that contain open interval that contain it. So we can keep moving forward finitely many times. Okay, but now we want to argue that this process will stop after finitely many steps. Okay, to cover everything. Does it make sense? Otherwise, we will be like what Pek Hong said. Between two numbers, we still have one number. Between two numbers, I still have one number. This is a bit like the Achilles of this paradox, right? Infinitely many number. Then I need to fill in infinitely many open set. Okay, then we want to prove that it's not going to happen. Okay, so how are we going to prove that? So let y, so this is our construction, let y be the supremum of a number from 0 to 1 such that we can cover it using finite subcollection of C. Okay. Can you see what we're going to do here? If this y equals to 1, that means what? If this y equals to 1, then we are done. Right? Because if y equals to 1, then that means 0 to 1 can be covered by finite subcollection of C. Okay, if it is 1, then we are done. So meaning what we need to do? We need to argue that y cannot be less than 1. Okay, we need to argue y cannot be less than. If y equal to 1, then we are done. Because the closed interval 0 to 1, I can cover it using finite subcollection. Okay, huh? Okay. So first of all, does this soup always exist or not? This soup exists. Why? Order above by what? Okay, order above by 1, and it is non-empty. Because just now we start with C1, right? Okay, we can cover up to epsilon already. Maybe a few more steps after epsilon we also can cover. Okay, so it's non-empty. And it is bounded above because the number you pick is going from 0 to 1. So it's bounded above by 1. Okay, so since the set, so let's call this set a name, okay? Let's call this set as soup of A. Okay, since A is non-empty and bounded above by 1, by completeness axiom, y exists. Okay, so now we not want to argue that y cannot be less than 1. Okay, we want to argue that y cannot be less than 1. So if y equals to 1, then we are the close for set of contradiction. Y is strictly less than. Okay, so what can we do here? So like Pei Hong said, right, any point I should be able to find one open interval that contain that point. Okay, so we can choose C0. Right, don't use the script C. This is a set of open set. So I'll choose C not in C such that Y is in there. Y is in C naught. What does this mean? Since C naught is open, it's an open interval, means what? There exists a, let's put it delta. Delta greater than 0, such that y minus, y minus delta, the open interval y minus delta to y plus delta, okay, is in C naught. Okay? And then this C naught is in the closed interval 0, open interval 0 to 1. Okay, we should be able to do that. What's next? What's next? Okay, so how should we imagine this picture here? So we have 0 to 1 here, okay, and then maybe y is in here, right? Okay, so we can have finite cover all the way up to y. And we can cover up to y plus delta. Y plus delta. Yes. Okay. So what's the contradiction here? Where's the contradiction here? Sorry? Y plus half delta. Yeah, what happened to y plus half delta? So, yeah, okay. So by definition of y, okay, there is a finite subcollection. Okay, let's say C1, C2 up to dot 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 some finite number Cn. Okay, from C, which covers where to where, which covers 0 to y. Is it y? But for sure, we can cover up to y minus epsilon over 2, for sure. And this is for sure. Okay. Remember, we're taking soup just now. We're taking soup. So for sure, you can cover up to y minus epsilon over 2. Okay. Not sure can until y or not. But what happens if I add C naught into this set here? What happens if I add C naught into this set here? What does C1, C2, dot, 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 out to Cn, C0 cover? Huh? It will cover all the way from 0 to y plus, so yeah, here is delta, don't mix up the epsilon. So y plus delta. Right or not? Do you see the picture here? See the picture here? Meaning what? Meaning what? Y plus delta is in the set A. So your supremum cannot be less than, your supremum is Y. Y cannot be less than Y plus delta. What is set A? Yes, what is set A? So we call this a set, the sup Y equals to sup of a set. We call this set A. So what is this set A here? These are the number in the closed interval 0 to 1, such that what? Such that the closed interval 0x can be covered by a finite subcollection of C. Supremum of X. Okay. Okay, no. Okay. So this contradicts the definition of Y. Okay. But just now I tell you that when Y equals to 1, right? We are done. Okay, but I didn't quite tell you why is it true. Why is it true? If the supremum, okay, of this set is 1, why are we done? Why are we done? Of course. But how? The question is how, right? The question is how. So if I say I can cover everything up to 1, okay, I can cover using finite set. How I cover the last part? 1 and maybe some epsilon away from 1. Find something what? Of course, sure. So what's that something? Huh? Okay, so let's expand this argument here. So let's try and expand this argument here. If y equals to 1, we also choose C naught in C such that C naught here will contain 1. Okay, what does this mean here? So meaning what? Meaning C naught cover 1 up to some, so 1 minus, let's say, epsilon, or some epsilon. Okay, the other way around, 1 minus epsilon to 1. Okay, but how we combine the C0 with the previous set to cover? Okay, yeah, how we combine with the previous open set, open interval, open set. Where do we obtain the previous finite subcover? Sorry, 1 minus epsilon. Is what? Okay, so by definition of Y, what is the definition of Y? Supremum of all the closed interval such that that closed interval can be covered by finite subcover. But you can simply pick 0 up to 1 minus epsilon, right? Right. So by the definition of y, 0 up to 1 minus epsilon, the closed interval 0 up to minus 1 epsilon, can be covered by finite collection of C. So I can cover everything up to 1 minus epsilon using finite subcover. I just add in C naught. Okay. Then the union of such finite sub collection and C naught will cover the closed interval 0 to 1. Does it make sense? Okay. 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 So where is the contradiction happening just now? The contradiction happenings when if you fix the supremum, then somehow this supremum you can extend again. Okay, you can keep extending, so you cannot find that supremum less than 1. So it must be 1. Okay. So this is a bit like the Achilles tortoise that you cannot go infinity within a finite interval. Okay. What time is it? 11:48. See. Okay, any question about this? Any question about this? If not, how about we prove one more property and then we will take a break. Okay, let's prove one more property. Okay. Next. So A is a compact subset of a topological space if and only if A with the subspace topology is a compact topological space. Okay, so what does this mean? Right? What does the statement mean? What's the difference between compact subset of a topological space and you are compact topological space with respect to subspace topology? What's the difference between these two? Can you try and imagine what's the difference between those two? What's the difference between these two? What's the difference between these two statements here? What's the difference between these two statements? Did we introduce a compact subset or not? Let me see. Otherwise, I'm talking bullshit here. Let me see, did we introduce it? We introduce, let me see. 15 compactness. Yeah, I think we haven't do it. So what have we done? So we only introduced what's a compact topological space. Okay. So how about so I think we need to introduce the definition first, otherwise we don't have definition to work with. So let's define a subset to be compact. Okay, so the set A in X is compact if and only if every open cover of A has a finite subcover. Okay. So a set is compact if only if every open cover of A has a finite subcover. So where does this open cover coming from? These are open cover, these are open set coming from X. And then you need to find a finite collection of them to cover A again. But what does it mean by compact topological space with respect to subspace topology? How do you get open set in subspace topology? Again, you take the open set in X and then intersect with your A. Sense? Okay or not? You can imagine what's this question asking? So let's say we draw some picture, right? Let's draw some picture. Okay, how should we draw this picture here? So let's do it in two ways. Okay, so what's the two ways here? So we got X and X, X. And then let's say we got A sitting inside, A sitting inside. Okay. So what does it mean by compact subset of a topological space? You are taking open cover, sorry, where is it? You are taking open cover in X to cover your A, and then you show that you can pick out a finitely many of them to cover A again. So meaning what? Let's say I can also include those open set doesn't contain A, right? Okay, but I can also remove them when I consider compactness. Does it make sense? Okay, but what does it mean by open in a subspace topology? You similarly you take open set in X and then, but this time you intersect with A. So how does the open set looks like here? The open set should really looks like something on the line. Is it very hard to see, huh? Wait, let me think. How should I do this? Let me change another color. So let me draw the intersection using orange. Okay, let me do it using orange. So what's the intersection here? So you might see open set like this. Make sense? Does it make sense? Make sense or not? Maybe I use a different color to see that this open set is coming from different intersection. Does it make sense? Compact subset in X. Pack in the subspace topology. In subspace topology, what set are open? Open set intersect with your subspace. So if you take your open set intersect with your subspace, then it really is some point on some subset on your A. Okay. Does it make sense? Make sense or not? Can you see a difference? Yongyan, can you see a difference? Can you tell us the difference? I don't want to ask you whether you can see, just tell me what you see. What do you see? What's the difference here? Surely color is different, right? Okay, so what does those color mean? Teacher? Not quite. Open set in A could be not open in X. Yeah, sure.
So why do I color these? What's the purpose of coloring here? What's this orange part here? It is the intersection of A is this line here with the first open set. Sense? Okay. So if we want to check compactness with respect to subspace topology, we need to look at this kind of picture. Intersection of open set with the subset. But if I just look at compact subset of X, I just use open set in X to cover A. Make sense or not? Does it make sense? Question? Any question or not? No? Okay. So, seems from this picture, right, it's quite obvious. Quite obvious, right? Is it quite obvious? Hey, how come you can make it? Just finish, Oh, okay. Yeah, so quite obvious, right? If I have a finite subcover here that can cover A, then you go and intersect it. I also should have finite subcover there. Okay. If I have finite subcover on the subspace topology, I don't look at the intersection. I just look at the normal open cover should also cover my A index. Does it make sense? So how should we write this down? How should we write this down? So how do we write this down? So if Cx is a cover of A by set open in X, so this is referring to the first picture here. So we have Cx, okay, cover A in X. Then you can consider, sorry, maybe we put a script here. So this is a set of open set. So we can put script A to be just C intercept A such that C is in Cx. So meaning if I can cover my A with an open set in X, then we can just intersect it to get a cover in the subspace topology. Correct or not? If you take an open set in X and then intersect with a subspace, it's already an open set in subspace topology. Make sense? Okay. So you can just really intersect it. Okay. You take the same circle, okay, and then just intersect it. And then this will form a, this is a cover of A by set open in the subspace A of X. So remember, in Cx, we are taking open set in X. But in Ca, these are open set in subspace. Okay. How to get open set in subspace A? I just take open set in X, intersect with A. This is what we defined last time. Subspace topology. You cannot ask why, because we define it like that. Okay, so this is the definition you need to know so that you will know what is this proof doing. But conversely, what? Okay. Conversely, if you start with Ca, okay, if you start with Ca, is cover of A by set that are open in the subspace A. How does this look like? Huh? How does the open set in the subspace look like? Then C in Ca looks like what? Looks like so intersection of A with a an open set in or some open UC in X. And we claim that, what do we claim? We claim that this UC will cover, this UC will cover, this UC will cover, this UC will cover A. Will cover A. Okay, this is our claim. Is it clear why it cover A? Why? Why? You got a bunch of intersection, so maybe let us write down. So what's the happening here? So we have A is in the union of C, I such that so this Ci is in Ca, but we know that how they looks like. So they looks like intersection of A with UCI. Okay. Then what? So I mean, we can rewrite this union and intersection thing, right? So we can rewrite it as A intersect with the union of UCI. So what does this mean? A is in here. Everything in here is in here. Everything in here is in here. So meaning A is in here. But if A have to be in this intersection, what does it mean? A already in A, that's fine. A have to be in the union of U. So they form a cover of A. Okay, so you see, everything here boils down to first week set theory. We talk about set inclusion. But the set we're looking here is very special. These are called the open set. If it covered it, then we'll call it an open cover. Yeah, if it contains the space, then we'll say it covered the space. Does it make sense? Okay or not? So I mean, to appreciate this argument here, right? You need to read it with this picture. Okay. So I'm not opposing you to use picture or any how to say. Maybe last time I saw you that you write layman term inside your assignment, right? But you how to say, you need to use some how to say figurative tools to help you to recall the full argument. Okay, because sometimes our logic is very boring, you know. But you cannot say you boring, then I don't want to study. That one is wrong. You still need to study, but logic with some figurative tool, then these two things will make a lot of sense. Okay, no? Logic itself very boring. If you just draw this picture, don't give me logic, you cannot convince me. But with logic, with figurative tool, then we can convince people at the same time it's easy to understand. Does it make sense? Can understand or not? Okay, so both you need to do. So this is the hard part of pure maths. Okay, you need to able to convince people. You need to be able to attract people. Okay. Any question about this so far? Not very hard, but a bit subtle. Okay, a bit subtle. Okay, so that means one of them is finite, then the other will have a finite subcover. So if and only if. Because I can transfer one covering to the other covering. Okay, if one of them can have finite subcover, then the other one will have finite subcover. Okay. Any question? Clear? Is it clear? Yeah. Got question? You can digest, okay. But any like that confusion, or not, at least not as much. Any confusion? Okay. You can digest, but make sure your line of reasoning is okay first. Okay, then you can digest. Otherwise, you're stuck at one point of line of reasoning. Maybe it's obviously false, but you just cannot get it. Then we can settle here faster. If even I also cannot settle it, then I can help you think about it. This is my point. Okay, in that case, let's take a break until 12:17 and we'll continue. Yes. Compact topological space is this. Free open covering of X has a finite subset. But just now I gave a compact subset definition. So compact subset, where do you get the open covering? You still get the open covering from X. But this time the open covering will cover A instead of X. And then that open covering will have a finite subcover. General. Which definition? Oh, this definition. Where's the different? Different is the subset. Any topological space. Yeah.
Open in A.
Open in X. Should be open in X. So if I'm saying it is open in A, right? Then this is what we're going to say. A with the subspace topology is a compact topological space. So here we think of A as a topological space. But how we think of a subset of a topological space as a topological space? We engulf it with a subspace topology. Then you can apply the compact topology definition there. So every open covering of A has a finite subcover. But what's the open covering A there? What things are open there? You have to be in the form of the intersection of open set index with A. So it is actually A is a compact topological space with the subspace. So try and think about the definition with this picture. And with this picture. So one, you just look at open set index. The other one, you look at open set index with the intersection of. Okay, so actually it's this color part. It's intersection, right? So anything not in the intersection, we disregard it. So this is the subtlety between these two statements. Gary, you can ask question if you want.思雨，有没有考试啊？星期三3个一起考。考什么？还有嘞，哦，也是拜师。去前面。哪一个？哪一个？
是粉红色的，
红色那个啊
那个再小一点
啊，
再小一点，
谢谢。哪一个？
可以下的，
什么？
我可以先走的啊，
你先走。哦，去哪里？
我放不进去。
然后不想说。哦，OK OK，再见。有要吃吗
有一点
？OK，
就是什么？S，C 是 A 的 cover 的时候，然后你写 A 等于 UN 解 set in C 嘛，它不是应该 subset 吗？你
在
然后
里，在里，
写等于
在里，在里。
不懂不懂，
对，应该要 subset。我在你写等于。
这些一直都是写的，
This means that。对，
这也是
是。对，没有错。Hello, testing. Remember this one the sub cover when I put equal right, it's wrong you don't need to be exactly equal. If you are a sub cover, you just need to contain. Just need to contain, not need to equal. You can imagine a closed set. If you want to cover a closed set, you cannot exactly cover it using open set. So you just require contain. So where else? I got this mistake here. So here also. Okay. Remember, when we talk about covering, I just contain. Just contain. Our definition should be correct, but sometimes maybe I write equal. Let's see our definition here. Wait, I think this definition got wrong, is it? Wait, huh? Oh, this is a space. Wait, let me see. So wait, some contradiction coming out. Oh, okay. So I mean, right. So so there's some subtlety here. So I mean, I think we really haven't introduced that yet. Okay, so I think we mix up some definition here. We'll talk about it. Wait, let me think. Where should we put it? You see, so the problem is here. Okay, and we want to talk about a compact subset, right? Okay, so how should we talk about this compact subset here? We only talk about a topological space to be compact. Okay, so really we need this definition. So what's this definition missing? So what sort of definition we're missing here? This. What's the definition we're missing here? So what is the definition we're missing here? You want to guess? So to define compact subset, what do we need? Open cover. Yes, open cover of subset, we need that. So what's the open cover of subset? So given a subset logical space. Okay. So what's the open cover of A in this case? Is what? It's also a collection of open set. But open in where? In X. Okay. But this time, this union here doesn't necessarily equals to A. Okay. Doesn't necessarily equals to A. Okay, so what does this mean here? So more precisely, A contains in the union of OC such that CI is in C. Yeah. Good. And then finite subcover is still the same. So you can define it as a finite subcollection of C, which is also an open cover of A. So meaning you use open cover of A again. So meaning I don't require equal, I require subset only. Okay. So if A is compact, then every open cover of A has a finite subcover. So the definition we're missing just now is open cover of a subset. But so just now we use equal, right? Unless you are considering the subspace topology. Unless if it is subspace topology, then you can get the equal sign. Otherwise, if it's open, then if you want to cover some closed set, right, you possibly need to include some extra point. At least from the example of a real line. Maybe you can prove for general. If I want to cover a closed set using an open set, would I always get? Sorry? What do you mean? Is it only one? Only one. Every closed set is also open. So every closed set, every open set. Then you don't need to include more point. Okay. Makes sense. Makes sense. Oh, so in discrete topology, every open set is also closed, you mean? That makes sense. Good. Next exam question. Or next time. Yeah, very good. Very good. Yeah. So you need to be able to like ask yourself some question and then try and see if you can prove it. If you cannot prove it, got counter example. Okay. This is a general way to think about maths. This is the right way to think. This is the mathematical thinking. That's what I want to say. So my first question will start with decide whether this sentence is true or false. This is the same as what I mean, every time I teach you a segment, right? You should try and think about already, verify whether it can be true or not, it can be false or not. Okay. You cannot just believe what I say. Yeah. You need to have your own judgment. Does it make sense? Okay. Yeah. Trend. You need to trend one. It's not easy. Okay. I'm trained for like 8 years already. You get what I mean? Okay, so it's not like one day, not like that one. You keep training. Train until even in the daily life you have to do that. People tell you something or judge true or false or counter example. Is he talking with logic or not? Okay or not? So this is the mathematical thinking we want to cultivate. Okay, it's not calculation. If calculation, robot also can do it. Okay, you need to cultivate. It's not easy, but you need to train. All right, good, very good. Let's continue. So let's continue. So what can we see here? So what can we see here? So so what can we see from the last statement here? So you are a compact subset in the topological space. If I look at you as a subspace topology, you are also compact. But this is not the case for open. For example, the half closed interval, okay, 0 to 1, is open in R. It's not open. But if you consider it as a subspace topology, then it is open because you can write it as an intersection between R and XL. But compact is not. If it is open, if it is compact in X, then if it is compact in the subspace topology. Okay, so compactness is what they call an absolute property. Okay, it doesn't depend on how we see it as a subspace or not. Okay, no matter where you put it, it is still compact. Okay, it's not like an open closed thing. And what else? But like last time we say, right, a subset of a compact set might not be compact. Okay, so it is not hereditary. Okay, so it's not like subset. Every subset of a compact set is compact. Okay, you cannot bring it down. We say down. Okay, bring down the subset inclusion. But what can we say? Okay, let's see what can we say more about these compact thingy. So first, what we can see maybe, let's do this one first, okay? But what we can see is if A is a closed set in a compact topology, the space, then A is compact. Okay, so meaning if you are closed in a compact set, then you are compact. Okay? So this is optional. So we have an additional condition here. You need to be closed first. If you are a subset of a compact set, you need to be closed. Okay, to be so that you are compact. Okay? So how to prove this? How to prove this? Not too hard. Okay, how to prove this? So okay, right. So because you want to show A is compact, right? First thing you need to start with is you need to start with an arbitrary cover of A. And then you show that you can find a finite subcover. How to do that? union sum open X. Union sum open set to cover X. Okay. So now my C can cover A already, correct or not? So just now, Ziqian say I want to cover X instead. Why I want to cover X? Do you know why? Huh? Why do you want to cover X? What property about X? X is compact, meaning what? Once you cover X, then no. What is about compact? Every open cover will have a finite subcover that cover X again. So you can like reduce the number of open set to cover your X. Correct or not? Okay. So I mean you need to have a picture in your mind, right? You cannot just think about set X, right? X is like this, right? Maybe A is something inside here is closed. Okay. Now you have some over cover of A. Okay, so how to cover X now? What's the thing you need to add to it? X minus A. Why we add X minus A? Huh? What is X minus A here? Is open. Consider X minus A. Is open. Why? Because A is closed. Okay. Then we claim that C, okay, C union with the set X minus A will cover A. Make sense or not? Does it make sense? Sorry, cover X. Thank you. So, is it true that it cover X? If it is in A, then surely it is covered by C. If it's not in X, then if it is not in A, then the complement will cover those points. So it's not a cover of A. So then we can use the compactness of X. So by compactness of X, C union the complement of A has admit a finite sub collection that also covers X. Okay, also cover X. But what's our goal? Who we want to cover in the end? A. We want to find a finitely many subcover that cover A. So how to find it? How to find it? Okay, what do you want to take? Say again? Just throw away X minus A. So take F, remove X minus A is a finite sub collection of C which covers. So what does this mean? This means that what did we do just now? What did we do? We just add X minus A into this collection. And when you want to make this collection finite, right? What you really do is you are making this collection of A finite. So in the end, you just really need the finite collection of C, right? Finite sub-collection of C, okay, that covers A. Okay, so what's the job of X minus A here? We want to include this complement of A to help us use the compactness of X to reduce, okay, to reduce the reduce the collection to reduce the open covering C. Okay, so that we can cover A with a finite collection. Does that make sense? Okay or not? Okay. Yes, question. Can we use a finite? I think you can. Yeah, I think you can. You can. You can. If you want to use F also can. Yeah, but you will. Yeah, you can use F. Yes. So there's some. So if you use F, then there's some observation here, meaning when you talk about open covering, right, you can add something extra into your covering actually. Maybe this empty intersection with your set. Maybe the open set has empty intersection with your set. Okay. But if it's compact, you can only do it finitely. I mean, you can always do it, but if you want to make sure it's compact, then don't overdo it. You can always do it. Yeah, you can always do it. Okay or not? Does it make sense? Yeah, you can use F more precisely, you can consider F throw away X minus A. Yeah, because it's just one thing. If you, one thing's or finitely many, you add one is still finitely many. Correct. Good. Okay, so it is not hereditary, but it is hereditary to closed subset. Okay? If you have a closed subset in a compact topological space, then automatically compact. So for example, what example? Okay, maybe we don't have good example yet. Never mind. So let's continue. So another thing is if A is a compact set in a Hausdorff topological space. Okay, recall what is Hausdorff, then A is closed. Okay. So what does it mean here? So if you are a compact set, meaning every open cover has a finite subcover, in a Hausdorff space, meaning what? Every 2 points I can, every 2 points in the topological space, I can take 2 open set that cover 2 points separately, and the open set are disjoint, good. Okay, then I can claim that A is closed. Okay. What is A is closed? There are few ways to talk about A is closed, right? There are few ways to talk about A is closed. You can use okay, we use limit point, close in limit point. If it's equal to its closure, A equal to A closure. What else? You can show that a set is closed. Or you can show that its complement is open. Also can do that. Okay, few ways to do it. But we're gonna use a strategy that let me put here. It suffices show that the complement is open. Okay. Right. So how are we gonna do this? So how to show a complement is open? Take 1 point in the complement and then show that there's a open. There's an open neighborhood that contains X, which is contained in the complement. Sorry? Sorry? Say again? What? No. We want to prove A is closed, but it's enough to prove X minus A is open. So meaning x minus a is open imply a is closed. Correct or not? Definition, right? Definition of closed. Yeah, it's fine. That's fine. That's fine. Yeah, this one, this is very important. Once you get this wrong, whole proof won't make sense to you one. Okay, so it's important to get the first step right. Okay, first step must be right. So to show that x minus a is open is what? You need to take a point in x minus a in the complement and then show that there's a open neighborhood that contain x and contain in the complement. Okay, one is contained, one is contained. ED. Okay, so how are we gonna do this? We're gonna do this. Maybe it's better we have some picture again. So let's get some picture up. So let's say this is our x. And where's our a then? So maybe we draw some a here. A, maybe like that. A. Okay. Yeah. So what do? We pick one point in the complement first. Okay, we want to try and show there's an open around x as contains at x minus a. Make sense or not? Can make sense of the picture and our goal and our assumption? Make sense, huh? Okay, so we want to find this open neighborhood. We need to find it. Don't know where to find it yet. Okay, find this B. All right. So what can we do here? We haven't really used Hausdorff-Nurse, right? Okay, we didn't really use Hausdorff-Nurse yet. So how are we gonna apply Hausdorff-Nurse? So the main problem here is we want to find a V that avoid A. Okay, I want to find a V that avoids A. Okay, can I do that? If I avoid A, then this whole ball will live inside the X. Correct? I don't want this V to intersect with my A because it has to live inside the complement of A. So how can I build this V so that I can avoid A? Avoid all. Okay, avoid means what? No intersection. Then this is where the Hausdorff have to comes in. Hausdorff can help you to separate. Okay, so what do we do here? So we can take any point in A first. I can take any point in A first. Okay, and then Hausdorff-Nurse says what? Any 2 points I can find open set such that they are disjoint and each of them contains separate point. So I can form I can form open set around this point here. Let's call it what name? Call it A. And then I can also find an open set around X such that their intersection is 0. Make sense? Okay. So how we call this name? We need to give them a name. Let's say the A one, I call it AUA. The X one, we call it VA. Can I just take VA or not? Why not? Maybe VN leave like this. Okay. So what do we do next? Pick another point in A. Okay, we can pick another point in A. So maybe this is let's call this one A1. Okay, these are all A1. Let me pick another point A2. Okay, A2, between A2 and X, you can also find 2 open set that avoid each other. VA2 And then this one is UA1. Sorry, UA2. Okay. Hey, this one you say, hey, very good, oh, very good. Why very good, eh? If I take the intersection of VA1 and VA2 still open, right? And then this two should avoid the two open set already. Yeah. So what? Overlap what? And this one is overlap around 1 point, not 2 point. This joint neighborhood is for 2 distinct points. X is a 1 point. Okay or not? Okay, huh? So you see, VA1 intercept VA2 is open, right? Then you think might be good, take this one. Because this one will avoid UA1, man. Can also avoid UA2, man. Can we just take the intersection or not? Can, Huh? Try. Sorry? Correct. So, you see, I mean, if you just take this one, right? This intersection maybe intersect your A again, right? So you need to consider every point here, inside here. Okay, and then look at the intersection of all such open set. But like what Soning said, maybe you need to consider infinitely many open set. What is the infinitely open set? What's the infinitely open set can get to? You might get to a closed set. But do we need to do infinitely many times or not? Why not? You just speak about an object. You haven't tell me the reason. The collection of UAI here should be finite. You just need to do it finitely many times. Why is it finite? Because A is compact. So for every point here, it only lies in finitely many open set. So you just need to compare finitely many open set. And then it will give you open finitely many V. Then what you do is you intercept finitely many V. Finite intersection of open set is open. And this open set will avoid all the points in A because it already avoid the open set. Okay, that contains A. Does it make sense? I think I don't want to write down the full argument. I'll write down in lecture notes. But I describe the process to you and then so that you can read the notes. Can get a process or not? Everyone got it? Okay. Yeah. Okay, so since so I write down the main point here. So since X is compact, they are finitely many U. Wait, hello, we haven't finished. You want to come and sit also can. Don't want. There are finitely many UAI. Okay, there are finitely many UAI. To consider, then you can choose V to be the intersection of finitely many V AI. Okay, does it make sense? Okay, yeah. Although there are infinitely many points to consider in A, but all these points are covered in finitely many open set. Then you just need to avoid these finitely many open set, then you can get your open set that's living in the very nice proof, huh? So you need to try and learn this. Very nice argument here. So what we have done just now, so we have proved that first we have proved that closed in compact is compact. Okay, then second, compact in Hausdorff is closed. Okay, compact in Hausdorff is closed. Closed in compact is compact. Compact in Hausdorff is closed. Okay, so this is the two things we're proving here. We have 4 more minutes. Let me see. Okay, let's do one more and then we'll see how it goes. And so combine the two result here, we can prove that if F is a bijective continuous function. Okay. So here is bijective continuous function. So how far is it away from homeomorphism? Inverse. Okay. So if S is compact and Y is Hausdorff, then F is compact. F is homeomorphism. Okay, so how should we prove this? What's the definition of homeomorphism is? Sorry. Correct. How about phrase in open set definition? Yes, F is open if and only if FU is open. Yeah. Okay, because this is about F inverse is open. Okay, so what does this suffice to show? So it suffices to show that instead of open go to open, right, we will show that close go to close is the same. Okay, this is the TFAE we established last time. So a closed set of X under F are closed. Note this is this direction is you apply F to a closed set in X, because for continuous, right, you need to look at the pre-image. Okay, but this one we want to show it for F inverse, so we go forward. Okay, so just need to show this because your F is already continuous, it's already bijection, so you just need to show that the inverse is continuous. So this is the statement you need. Okay, so what do? We start with a closed set in X, correct? No? Okay, then we want to argue that FA is closed C. Okay, it's closed. So if A is closed in X, what happened? X is compact. So just now, what did we show? Closed in compact is what? Compact. So this means that by previous theorem, A is compact. What's the continuous image of a compact set? The first thing we proved today. Okay, so therefore, FA is compact. But Y is what? Hausdorff. Compact in a Hausdorff space is closed. Since Y is Hausdorff, FA is closed. Okay, so you see, to show this homeomorphism, you don't need to go through what epsilon delta, what like that. What do you need to know? Okay, first, I think quite rich already. You are bijective continuous function. So meaning what? You need to check first your function is bijection. Okay, you need to show that the F is continuous. Okay, this is what you need to show. But sometimes if you want to check the inverse, remember the example I gave you last time about the homeomorphism between the disk and the ball, the disk and the sphere, correct? Not the quotient map. Okay, if you have to consider the inverse, how to consider? What you remember? What map I gave you last time? sure you still remember or not. It's like the composition of a three-go map. A lot of three-go map. If you want to go and find the inverse, I think it's pretty ugly. Up sign, so what, and so on. Right or not? Wait, let me show you first. Otherwise, the thing I'm singing here. Yeah, this one. You see? So the forward map is already quite complicated. Okay, but still fine is a product of three-go. But how about the inverse? Okay, how about the inverse? Okay, inverse of this such map here. You see, inverse is quite. I think this one is still fine. Okay, but what I want to say is checking continuity is quite a troublesome thing. Maybe checking inverse is also very troublesome. But if you happen to know that your space is compact, okay, your domain is compact, and your core domain is Hausdorff, okay, no need to check your inverse is whether it's continuous or not. Then this theorem will tell you that it is continuous, okay, just by the space property, okay, property of space. Does it make sense? Okay, no. Okay. I think later when we do 1-point compactification, then we can use this theorem on our example last time, the quotient map. Then we can talk again how we apply that. Okay, because okay, we can revisit the example again. All right, any question before we break? Question? So hopefully I will see you on what day? Wednesday. Yeah, Wednesday. So if there's nothing goes wrong, then we will return exam, discuss exam on that day. Can see you on Wednesday. Oh yeah, the assignment is out, by the way. You can start now.
一起加入一个群。